Good afternoon and welcome. We're here today for a webinar. The subject matter is PLC Basics. My name is Dick Yeomans. I'll be one of the instructors, basically doing the introductions. Our main presenter will be Clayton Wilson of Yokogawa. A little bit of history about the two companies. Yokogawa is a global network, 59 countries, including 114 companies. They were founded in 1915. The U.S. company is a pretty good sized company, $3.7 billion, engaging in cutting-edge research and innovation. They're active in the industrial automation and control market, IA industry, testing and measurement, aviation, and other business markets. I mentioned that IA segment. It plays a huge role in a very wide range of industries, including oil, chemicals, natural gas, power, iron and steel, pulp and paper, pharmaceuticals, and food. So it's a pretty massive conglomerate. David H. Paul has been a world's leader in industrial water treatment training, high-tech water treatment training since 1988, specializing in membrane treatment, microfiltration, ultrafiltration, nanofiltration, reverse osmosis. We also cover ion exchange, EDI, and much more. Our training consists of online training. We also have classroom and hands-on training seminars that we can provide at our facility, or we can come to you at your facility for the training. We also have technical services, which includes membrane autopsies, troubleshooting and consulting, as well as reviews, requests for proposal reviews, cost edits, and much more. DHP and Yokogawa have joined together for a series of webinars for the last several months. PH Basics, ORP, PH-ORP troubleshooting, conductivity, and PLC Basics. You can see we've done one every 2 or 3 weeks for the last several months, and the subject of our 5th and final in this series is PLC Basics. It's going to be about a 45-minute presentation, give or take a little bit of time. Like I said, I'll be providing the introductions. Clayton's going to do the heavy lifting. He's going to provide the details. At the end of the presentation, we will have hopefully 10 to 15 minutes of questions and answers. So at any time during the webinar, type your questions in the questions box, and they will be addressed at the end of the presentation. It will be recorded. This will be available on our website sometime later this week, probably early next week. You'll be sent an email thanking you for attending, which will include a PDF of this presentation and a link to the recorded webinar. It's important to understand that David Paul and Yokogawa do not have a financial relationship. We don't endorse each other's products. We're not promoting each other's products through this webinar. We are simply presenting this information as a service to the water treatment industry because of the particular interest and the potential value to both of our clients. My name is Dick Yeomans, as I said earlier. I've been in industrial water treatment since 1977, specializing in membrane technology since 1998. Therefore, I've trained and consulted at, I don't know, hundreds of plants by now. I am a certified water technologist, certified through the Association of Water Technologists. I am also reverse osmosis level 4 certified through David H. Paul Incorporated. Clayton is currently the product manager for discrete control instruments and the nuclear industry manager. Been with Yokogawa for 24 years. His previous experience was with NCR, and he has a BS in Electronics Engineering Technology from DeVry Institute of Technology. So, as I mentioned earlier, at any time during the presentation, input your questions in the question box. They will not be answered immediately. They will be answered at the end of the presentation, and we're going to cover as many of those questions as we can. Any of the questions that are asked that are not covered will be answered by an email, and they will be included in the recorded webinar.
Okay, thank you, Dick, and thank everybody for who's in attendance, and hopefully I can give you some good information on the kind of the basics of PLCs. And again, my name's Clayton Wilson, as Dick was saying, and I am the product manager for the discrete control products at Yokogawa, and I've been with them for 24 years. So PLCs are really a wide product, and I want to say it's a wide area and can be used in a lot of different applications. And there's no way in the world within 45 minutes we can discuss all the points of a PLC. So we're just going to kind of discuss some history and some basics today, and hopefully give you an understanding of where the PLC came from and what its primary purpose is, and hopefully give you some ideas about moving forward if you're looking to implement a type of PLC solution. Give me a second, let me get my presentation started. Hopefully you can all see that now, so let's go ahead. Okay, since about the 1960s, the Programmable Logic Controller, or PLC, has become an essential aspect of any automated process. In recent times, there's been contenders to replace the PLC and expand functionality added to the PLC, but the principles and popularity of those early PLC functions and concepts have continued unabated. It's essential for many people, from the technician to the engineer, to understand these essential concepts. PLCs are used in many industries and many applications, such as oil refineries, manufacturing lines, conveyor systems, and many others, and we'll talk about those in a little bit. Wherever there is a need to control devices and automate processes, the PLC provides a flexible way to what we call softwire components together. And that word softwire is the real power in the PLC. Okay, so let's take a look at this example. In this system, with the flick of a switch, the light would come on or it can be turned off. Beyond that, there's really no more control to this. But if your boss came along and said, hey, I want that light to turn on 30 seconds after the switch has been flipped. To accomplish this, you would need to buy an external timer and do some rewiring. So in doing that, there's time, there's labor, there's money to do a simple change like this. Now let's add a PLC. The switch is fed as an input into the PLC, and the light is controlled by the PLC output. Implementing a delay into the system is easy, since all this needs to be changed is the program inside the PLC and the use of the delay timer as far as one of the functions in the unit. So for something this simple, you're asking, would I really need to use a PLC for something this simple? Yeah, probably not. So let's go to a more real-world example. Let's suppose there's a closed tank where there could be a pressure buildup. A solenoid is powered to keep a release valve shut. Every time the pressure sensor is tripped, a solenoid is deactivated for 10 seconds. That, in turn, allows the relief valve to open and the pressure to be released. After 10 seconds, power is restored to the solenoid and the valve is closed. Also suppose that the process needs to count how many times the pressure is released. Without a PLC, the process would follow this diagram, the one here at the top. The pressure sensor would feed information into the timer and counter, two separate pieces of hardware. The timer would disengage the solenoid at the time until the time is elapsed, then re-engage the solenoid. This is generally pretty simple and does not require too much work. Now, let's assume that the process includes 50 sensors and 50 solenoids. We need 50 timers, 50 counters, and what if a manual release button or other safety sensors were also needed? This situation can quickly become complex and involve a large amount of hardware. If any one of the units failed, the whole system would have to be shut down. The fault would be found and then fixed. Before PLCs, this is how that was done. This photo was typical of a large control system or a large panel full of relays, timers, counters, switches, the whole 9 yards there. several problems with this type of scenario. One, if you're building a new system, you have a long construction time to mount, wire, test, all of this hardware that's going into this system. Number two, it's difficult to troubleshoot because the larger it becomes, the more wires, interconnections, all of that increases and becomes more difficult to troubleshoot and to fix. Making changes is difficult. Can you imagine having to integrate a couple new relays into a control room system like this? It becomes a daunting task. And it can become costly because of the additional parts, the labor, the troubleshooting, the engineering. So this is typically where things were before the PLC. And the need for the PLC was born out of this. So the PLC replaces all the wiring and individual pieces of hardware like counters, timers, relays, etc. With a PLC, all the wiring is done in software. And that's what I mentioned earlier about the soft wire. It's done in the software, and all the components are software routines. This adds an additional benefit that if a change is needed, no one has to come and disconnect wires or move hardware around. This can be very time-consuming and tedious. The only thing that has to change is the PLC's program. It needs to be updated and then loaded into the PLC's memory. And if there's a problem and the PLC breaks, well, we just replace the PLC. The basics of a PLC is relay logic. A relay is an electromagnetic switch operated by a relatively small electric current that can turn on or off a much larger electric current. At the heart of a relay is the electromagnet. The electromagnet is a coil of wire that temporarily becomes a magnet when electricity flows through it. You think of it as kind of an electric lever. You switch it on with a tiny current and it switches or leverages another appliance using a much larger current. So why is that useful? As the name suggests, many sensors are incredibly sensitive pieces of equipment and only produce small currents, electric currents. But often we need them to drive much bigger pieces of equipment that use larger currents. Relay bridges, the relay bridges that gap, making it easier for the small currents to activate larger ones. That means relays can work either as switches or amplifiers. This is an internal diagram of a relay. The green cylinder is the electromagnet or coil. As a small current is fed through this wire-wrapped coil, the coil becomes a magnet. The magnetic field attracts the armature, and its motion changes the state of the contact, which are there at the top. Depending on the relay type, the contact will usually have two states of operation, normally open and normally closed. These are the conditions of the contact when no power is applied to the coil. So depending on the logic required from the process, when a coil is energized, that would determine which contact you would connect it to. So also, the ladder logic symbols represented in the action of the relay have been placed on the screen. So I kind of put those there so you can kind of see, because we'll be looking at those a little later when we look at the ladder logic diagrams. The coil is being represented by the circle with the wire connection. The normally open contact being represented by two plates separated by a space, meaning basically there's no current flow or no connection. The normally closed contact being represented by the same two separated plates with a line drawn diagonally through the plates. And this indicates that there's a short between the two plates and that current can flow through them. And again, this is the basics. Anytime you're seeing this in a ladder logic diagram, that coil, that normally open contact or that normally closed contact, what you're doing is you're looking at basically a relay such as this that's being replaced by those symbols or by the program in the ladder routine. So typical PLC applications, where can I use this thing? Well, realistically, as PLCs become cheaper and cheaper, some PLCs you can buy online for less than $100, and if you're a fairly decent programmer, you can take some of those small Arduino modules or small microcontrollers and build your own type of PLC. but they control a lot of things. Coin-operated car washes, traffic lights, crosswalk control, elevators, amusement park rides, automatic doors. Realistically, there's a lot of things that are being automated in today's world that really the PLC is doing that work for us, and many times we're not even thinking about it. So let's talk a little bit about the basic components of a PLC. There are four main components of a PLC: the inputs, the outputs, memory, and the control program that resides in the memory. The inputs are connected to sensors that inform the PLC about its environment. So the program allows a set of logical instructions that drive the outputs based on the inputs, and the program replaces the wires, the relays, the hardware. So that's the kind of the meat of the PLC. The outputs are connected to the equipment that need to be controlled. The memory contains the user's program, the program data, storage, PLC operating system, that type of thing. These basic components have various parts within themselves depending on the PLC manufacturer and the options they have for that PLC. Inputs can vary widely, just depending on, because there are so many components out there in the field, and they all have different output requirements that need to be read by a PLC. So PLCs can have TTL inputs. They could have 12-volt DC, 24-volt DC, 120-volt AC. They can have voltage pulse inputs, analog. I mean, as many types of devices there are with different types of outputs, the PLC can have those different types of inputs as well. And that's also going to depend on the manufacturer. So certain manufacturers may favor certain inputs over others. The larger manufacturers typically going to have more input types, where the smaller ones you're typically may be stuck with TTL or some analogs at the maximum. Outputs widely vary as well. They can have just as many options, and what they do is they connect to items in the field. Inside the PLC, the program runs on a small computer or microcontroller, and its only purpose is to execute the program that's placed inside of it. The size and power of the controller is determined by the manufacturer based on the number of IOs required, the size of the program that will be installed, and the speed the programs need to be executed in. And those variables are determined by the application or the marketplace that the PLC vendor is planning to sell the product into. So again, that $99 PLC you're going to find online, you're not going to use it to control a high-speed bottling line, because number one, the I/O that's required may not be enough, as well as the speed may be maybe too slow to read the sensors and control a high-speed line, where several hundred pieces of equipment are flowing past in seconds. Since a PLC is a dedicated controller, it will only process this one program over and over again. One cycle through the program is called a scan, and involves reading the inputs from the modules, executing the logic, and then updating the outputs accordingly. The scan time happens very quickly, in the range of milli or microseconds, again, depending on the vendor and the primary design for that PLC. The memory in the CPU stores the program while also holding the statuses of the I/O and providing a means to store values. All right, let's talk a little bit about the I/O devices. All right, as far as the input devices, the inputs can be digital, analog, or a combination of the two. As we talked earlier, this is the way the PLC touches the real world and how it sees what it's trying to control. So, and again, there's many different sensors that are out there on the marketplace. The PLC has a variety of different inputs that can be taken into it. Digital card handles discrete devices, which gives a signal that is either on or off, such as a push button, a limit switch, or selector switches, these type of things. So it's very common. And analog input card converts a voltage or current into a digitally equivalent number that can be understood by the PLC. So as the PLCs have grown and time has gone on, digital inputs and outputs have morphed into analog signals where, in essence, it's still all digital. PLCs, there's not really anything analog. You can bring an analog signal in, and a circuit in the PLC changes that analog signal into a particular digital signal. But in essence, we can still approximate what that analog signal is, and it's understood by the PLC, by the CPU. These digital signals can be physical or virtual. So we can bring them in with the push button, or again, as we go into the later PLCs or some of the PLCs with more options, some of these PLCs can bring data in over communication lines, and we can turn on switches and relays and that type of thing over a digital network. One type of thing or such thing, and we're not going to talk about this because I think this kind of goes beyond that, but this is very common in the PLC marketplace, are HMIs or touchscreens or computer interfaces where the information being fed into the PLC is coming from one of these items, or an operator is changing set point values in a touchscreen, and the PLC is operating from that. So again, this is one type of input device. And again, I didn't mention it here. Maybe I should have, but I was, guess I wasn't thinking hard enough at that point. So again, here are some examples of some physical PLC input devices. We have push buttons, photo sensors, pressure sensors, temperature sensors. Again, it's a wide variety of different input devices here. And we can say the same thing basically about the output devices. They consist of also analog and digital types. A digital output card turns a device on or off, such as LEDs or lamps or relays, that type of thing. And if you're using an analog output, that card does the same thing as the analog input card. It takes a digital value and converts it into an approximation of an analog output, so that maybe you're sending a 4 to 20 signal out of the PLC into a display module. And you're not able to send a digital signal, you send the analog signal. It can approximate that signal between 4 to 20 by using a D to A converter inside the PLC. And again, here are some examples of some output devices: motors, solenoids, relays, or contactors. And again, I showed you that contactor or that relay in the previous example. Yes, PLCs are designed to replace the network of relay logic that was found in a lot of the control applications. But still, the relay contactor is one of the most common output devices you're going to find, and input devices, to be honest with you, you're going to find in the marketplace or in industry, because again, their utility is so widely used and so widely accepted. So let's get to the meat of this, of the PLC ladder logic, and that's really where the PLC shines and the major portion of this occurs. PLC programming is called ladder logic. It's not the usual type of programming you may have been used to, such as BASIC or assembly language. It's a programming language that uses the graphical symbols to provide the PLC with logical instructions that are needed to perform control operations. So learning how to use and implement PLCs is basically learning ladder logic. So as we discussed earlier, when PLCs first arrived, they were made to replace relay hardware. They were designed so that a minimal amount of retraining would be needed for the engineers and technicians to operate and implement them. So with that, the ladder logic was developed to mimic relay logic diagrams. So, and when you're looking at a ladder logic program, that's what the ladder logic program is going to look like. It's going to look like relay logic schematics. And again, as the PLC has come more and more into favor over the years, and it comes into favor since it's the 60s, so it's been here for generations. A lot of those relay logic schematics, you're seeing less and less of them, but they're still out there. I mean, in wide variety. But a lot of the PLC programmers are not copying those so much. They're coming out with new diagrams and that thing from their own memories and from their own experience, and reusing existing programs. So if we take a look at this, this is an example of an actual ladder logic program and a logic relay diagram. On the left, the logic relay diagram actually shows in a schematic how the sensors, the counters, timers, outputs are to be wired in a control scheme. On the right is a small program that I put together for a ladder logic, in ladder logic. And if you look at the two, they're not exactly the same, but they look similar. You can see the relays here on the left, or the contacts on the left, and on the right-hand side, you can see the coils. And basically, if I were to implement this pressure sensor, and I think this is the example I used earlier in the presentation, we could build this just as it is in the ladder logic program and have it operate properly. So it makes, again, with the engineers and the technicians who are looking at these relay logic diagrams, it's making it very easy for them to look at that and implement this control scheme into a PLC. So again, we're saving time, we're saving energy, and we're not having to retrain them on how to program in ladder logic. And the reason it's called ladder logic is because the diagram looks like a ladder. Each step in the program, and that's called a rung. The vertical lines on the left and right are the power rails. So this represents the power in the circuit that energizes the coils and provides current flow through the contacts. So in many cases, on a true relay, you're going to have a small current that's actually going to energize the coil, maybe a 12-volt signal with a small amount of current. And then on the contact side, you may have 120 volts and 45 amps. But on a PLC, you only have one set of power rails, so we don't really care what the voltage is. It's just that is power being passed from one side to the other, and so that you're only going to have two power rails, regardless of what the voltage is in the relay. And each rung is going to define one operation in the control process. The ladder diagram is read from left to right and from top to bottom. And each rung starts with one or more inputs and ends with an output. So the inputs, or the contacts, are going to be on the left side, and the coils and the outputs are going to be on the right side. So there are also quite a few manufacturers of PLCs, and each one of these has its own brand of ladder logic programming, but they're all very similar. And if you can program one, you can program the other. And so there's the training, again, that was designed so that an engineer can go from one to the other with not a lot of problems. Yeah, there are a few features that are a little bit different, and the way they implement the ladder logic, especially when you get into some of the later features, such as, and I don't know if some PLCs like Yokogawa have embedded PID control, and the way we implement that is different than somebody else might implement it. But that is a more advanced feature that was implemented after the relay logic was implemented into a PLC. So so you may find differences in those things that are non-standard relay type of functions, but the basic relay logic is going to be the same. Your contact, your power rails, your coil devices are all going to look and feel the same. So on this page here, you've got a few of the standard symbols: the power rails, open and close contacts. Power is always said to flow from right to left, and power flows through an open or closed contact depending on the input condition. If power can get to an output device, it turns on. Contacts are always on the left side of the ladder, and power and output devices are always on the right side. The contacts and the output devices can be either real, inputs and outputs to the PLC. They can be special functions. The ladder program can be the status, but okay, I'm sorry, they can be special functions of the ladder program, but the status of the words in the PLC memory, I don't know what I was, but they could be any of those things. Okay, so let's take a look at the Boolean math. Boolean is an interesting thing. He was a mathematician back in the 1600s or something like that. He was a long while back ago. And he developed a form of binary algebra. So it is a form of algebra, but the thing about this algebra is it deals with ones and zeros only. We're not looking at large quadratic equations or anything like that. It's simple ones and zeros, and it fits nicely with relay logic, as you know, all the inputs and outputs are expressed as ones and zeros or ons and offs. It became a really good tool in dealing with computer science and programming and with PLCs, because it allowed us to check the math or the logic using pretty much standard mathematical equations. So by using the Boolean, and it's something that's really not used enough anymore, but I want to show you a little something about this, and hopefully you'll see why it makes sense to do this. But this is a tool that engineers used to use when they were using relay logic, and again, it's becoming less and less out of favor now as PLCs have pretty much dominated the marketplace. So in looking at Boolean logic, there are several functions. The simplest of all the functions is the NOT gate. And what a NOT gate is, its only purpose is to change the condition of what's coming into it. So if you put a 1 into it, you're going to get a 0 out of it. And it's really no simpler than that. On the right there is a little box with a set of conditions. It's called a truth table. And I'm going to explain it here, but as you see some of the other slides, you're going to see how that truth table gets larger and a little bit more complicated. So if we take that symbol there, the triangle symbol with the dot on the end of it, which is basically a NOT symbol or an inverter, we put a 0 on the input of that. On the output of that, we're going to get a 1. If we put a 1 there, we're going to get a 0. And again, this is a very common function, and it's very necessary in dealing with relay logic. If you look there below that, that's a contact signal with a line through it, which is basically indicating they normally closed. Basically, it's telling you, hey, whatever's coming in is going to be the opposite. So when we're looking at the relay, a relay with no voltage on the coil, you had two conditions. You had a normally open and you had a normally closed. The normally open with the contact open was the normal state. The normally closed allowed current to pass. In this case, a NOT represents that contact that's closed when there's no power applied to the contact, to the coil. So it's just, I wanted to show that so you can kind of understand how the NOT function and some of the other functions correspond to the Boolean logic that's here. Okay, an AND function. This is a function that would be used when multiple conditionals must be met before an output or a permissive is given. For example, a simple example would be like a closed dryer at your house. As you know, if you don't close in the dryer and you get ready to turn the dryer on and the door's open, but you press that start button, nothing happens. You have to close the door, and if you look closely at that door, you'll see a small switch there. When that door closes, it engages the switch, and at that point, you can turn the dryer on. Yeah, there are other things involved with that as well, but just as a simple example, it's telling you that, hey, both conditions have to be met, the door closed and the button pushed, before we can engage the motor that turns the dryer. So that's what this is showing here. So the symbol there is kind of like a D with a couple of inputs and an output on it. But in ladder logic, the symbol below are two contactors in series with one another. So again, a very common symbol here. So two contacts, if A is true, but B is not true, there's no current flow. Both A and B have to be true. And if you look at the truth table to the right, you've got column A, B, and the output. The only condition where the output has a true condition is where input A and input B both are true. So again, this is the function of the AND gate. And looking at a simple circuit here, and again, going back to the dryer, this is not the on, but this is actually the heating element control. We're looking at the same thing, and at the bottom there are your series of functions that have to be true before that heating element, which is highlighted in yellow, can actually come on. So the first thing is the timer heater contact. The timer contact has to be, so you have to turn the timer on, so the timer has to be engaged. There's a thermal cutoff, which is more of a fuse, but as long as we haven't overheated the unit. The operating thermostat, as long as the temperature is below the set point, that contact's going to be closed and allow power to flow. The high limit thermostat, as long as it's not over temperature, is going to be closed and allow current to flow. And then you have the current flowing through the heating element. And to the right of that, you have your motor control. In essence, that switch is your pull-in switch. When the motor is turning, it pulls that switch in. So as long as the motor is running, the timer is engaged, the temperature is cooler than the set point. When you hit that start button, the dryer heater will heat up and dry the clothes. The operating thermostat, as the temperature rises, it will get to a certain temperature and it'll open up, saying, hey, I don't want to add any more heat, I'm already too warm. And that allows the temperature to fall and that the heating element shuts off. So this is a sample of a AND gate or a simple AND circuit. So again, just something that you say, hey, this is something that we use very commonly, and then there's a lot of other applications in your home, your car, your job that use this type of functionality. And I won't go into too many more details about most of this stuff, but I do want to just kind of mention some of the others. Another very common one is the OR function. This would be used when only one of multiple conditions must be met before output permissive is given. So both of them don't have to be true. If A comes on, you get an output. If B comes on, you get an output. If A and B come on, you still get an output. So as the ladder diagram shows here, there's two pathways to an output, and only one of them has to be true for that to occur. So here we have what we call NAND and NOR functions. And basically, they're just a combination of the functions that we had previously. We had an AND gate and a NOT gate that are tied together. Then the NOR function is an OR gate with a NOT function tied together. And that NOT function is indicated by that little dot at the end of each of those symbols. So, and that's really all this is saying here. It's just saying that this is an invert from the what you would normally have in a circuit. Now, the NAND and NOR functions indicate that the output is inverted, but the NOT function can be put on both, on either the inputs or the outputs, or it could be on both. You can have input A NOT, and then a normal B, and then the output inverted as well. So there's a lot of flexibility in how these logic circuits work and what you can construct with this type of logic type of diagrams. Another function here is the exclusive OR function. A little bit different. It's like an OR function where it's one or the other, but it's exclusive to one or the other. So you can have A on and you have an output. You can have B on, you would have an output. If you have A and B on together, there is no output. So you probably use this type of function and not even think about it. If you have like a room in your house that works on a light switch, that works on two light switches, not just one. If both light switches are in the same position, then the light will be off. But flipping one or the other will allow the light to come on. So if they're in the same position, they're off. If they're in separate positions, the light comes on. So this is an interesting function for the exclusive OR. And light switches is one thing, but there's a lot of functions that go on with relay logic where the exclusive OR is used quite extensively. All right, so I'm almost done. I know it's getting a little complicated here, but I just want to kind of go over this and show this because this is really not used too often in industry anymore. It's very important, I think, to use it, but I think a lot of programmers go through this and say, you know what, I don't need to do that Boolean stuff anymore, but it does show something here. So what's the practical application of this? So let's take this example. At the top is a logic diagram for an industrial process. Let's assume it's a safety interlock. And the process has 3 inputs and 1 output. The expression above that is it represents the circuit in Boolean math. So if you look at that A, B, and C of the inputs, that A with the line over it or A naught indicates a signal coming in and inverted. The B just indicates a normal signal. And if you look there in that first A naught plus B, represents that first OR gate there. So, and again, it's one or the other, so it's A plus B. And then the second expression, A plus B plus C, represents that OR gate right below that with the 3 inputs. And you see all 3 expressions, quantity A plus B, A naught plus B, times the quantity A plus B plus C, times the quantity C naught. And that represents that AND gate at the very end. So it's kind of how that expression is laid out there in Boolean math. So if we get an expression set up like this, and again, we're still looking at algebra, if we expand this expression using the associative property and reduce the common elements, we're able to boil this expression down to a much simpler expression. And that simpler expression is down there at the bottom of the page, which is B naught C. And I'm not going to go through the math, but if you'd like to have a presentation, you can take a look at it and work it out. It actually works out that way. So in the past, this exercise was routinely done as each component in the circuit represented 1 or more pieces of real hardware. So you had to construct that, to build it, test it, and the widespread of PLCs kind of stopped this routine, and people skipped it since there's no real hardware cost involved anymore. When you were spending dollars on buying hardware for each multiple AND, so you got OR gates, that's at least 2 relays. The OR gate, the AND gate here is at least 3 pieces. That other OR gate is at least 3 pieces. There was a reason, because the more unnecessary logic you had in the circuit, the more the cost was, and the longer the time was to construct it. So you wanted to boil that logic down to the least common denominator to ensure that you had the functionality that you needed, but you weren't wasting time and money doing that. So there is a good reason to continue doing this exercise. So if we take a look at this, on this page here, we know both circuits are equivalent and will perform the same function equally as well. But if you take a look at this, what we discover here is with the second one, or the reduced circuit, the B naught C, what we're missing there is the input A. Input A has no effect on the process, even though on the top diagram it's going into 2 circuits, one being knotted, one being not knotted, not being inverted. So let's assume we go back to our earlier example of the closed tank that was building pressure. If that A input line was some type of safety monitor for the tank, that input would have no effect on the process and could potentially cause a hazard. So it's really important to ensure that the logic that's written is actually performing the function that it was intended to. And the Boolean math here that we just kind of, the little exercise we did was a great tool for trying to determine that. I also on the right hand side placed actual diagrams of these circuits to the right, so you can see that the reduced ladder logic program is much simpler. It's just a single line of code, whereas the original used here, it looks like 7 lines of ladder code. So that it allowed you to kind of economize the programming, if you might say, so that rather than writing the extra lines, you can get right down to the function that you're looking for and program it quite easily. As well as you've got that rogue A signal that's no longer affecting the process. you can much more easily implement that into the second diagram versus trying to figure out how that first diagram works and trying to ensure that your safety interlock is working properly. So, okay, well, it looks like I'm right at 45 minutes. I guess it's 12:45. So that's just a basic overview, guys. There's a whole lot more to PLCs than this, but I just wanted to hit on some really basic ideas and just put them out there for you. And hopefully this was helpful in some form or fashion. So at this point, I'm going to turn this over back to Dick, and thank you for listening.
Okay, now we will move into the question and answer.
Okay, looks like I've got a question here. What is the typical lifespan of a PLC? Additionally, when would you recommend upgrading to a newer model versus just a replacement? All right, so typical lifespan of a PLC. It's quality is a big issue in instrumentation, and in essence the process that you're going to use it in. And I'm gonna say this, that all things being equal, I would choose a higher quality PLC versus a lower one. The typical lifespan is, again, it's going to be based on how it's constructed. You get what you pay for. Let's just say that. I've seen PLCs that they've been in the marketplace and they've run 20 years and they're still operating with no trouble. Then there are PLCs that you put in and they run and they're on skids and you've got to replace them after a year and a half. So it's just going to depend on the quality of the product you're going to buy initially. Now, again, when would you recommend upgrading to a newer model versus just a replacement? Again, that's going to depend on what you're looking to do with the PLC. For the most part, in most general, if you're working with let's say you're dealing with a bottling line and you're measuring number of widgets passing by a point and you're controlling the conveyors and the PLC you're using is working just fine. Why would I upgrade that? Number one, if you want to add additional I/O, more I/O, you want to upgrade that, because some PLCs are based on the number of I/O points. So the higher the I/O, maybe you have to have a higher processor. The next thing is going to be the communication interface. So if you want to talk to a PLC, maybe you were using RS-485 Modbus. Now you've upgraded other aspects of your process or your plant, and now you want to talk to it over DeviceNet or Profibus, or not DeviceNet, I would say Ethernet IP. That's still an old protocol. You would then need to upgrade or possibly upgrade the PLC to get the higher protocols. What is neat about this, though, and especially PLC since they're modular, is you can remove maybe just one or two components of the PLC and keep maybe the I/O that's already connected. So maybe a CPU and a communication module can be replaced, but the backplane and the support structure is still there, and you just add on new components to increase the capability. So it's not like there's a completely new investment that has to be done, just more of an upgrade there. So hopefully that answered the question. Can a PLC work in wireless mode? For example, a simple Raspberry Pi can be used as a PLC. Wireless mode, sure. I mean, the fact that you want to put remote I/O, and I'm assuming it's remote I/O that you're looking at, and having it connected wirelessly to the process, that shouldn't be a problem. There are a variety of different radio solutions on the marketplace that would allow you to talk back and forth to remote I/O on a process. Now, here's the thing about that, and that's going to depend on your threshold for pain. If this doesn't work, or there's a problem with the wireless connection, or if there's a possibility that that signal could be intercepted by somebody who may have bad intentions, that I always say you don't want to control a process remotely. That is a critical process. I think it's a great idea to pull data from certain points from the field over wireless, but I don't think it's a great idea to try to control a process that has critical implications over wireless, just because there are too many factors or variables that could prevent or could cause a problem with that. So that's just my personal opinion with that. And can you use a simple Raspberry Pi as a PLC? Sure you can. Again, there are many programs online that people have used Raspberry Pis to do types of control. Absolutely. I've never done that before myself, but I know a lot of people who have. And again, if you go to YouTube, there are tons of videos that actually show how they've done that, and you can download the code from online very easily. Okay, I have a Fanuc PLC on one of the reverse osmosis units. The HMI does not respond at all to the measurements that are in. Communications is lost. Wiring is fine. What could be the problem? Okay. A couple things with that. First question I would ask is, was it working initially? And I don't see if the HMI does not respond at all to the measurements that are put into it. I'm assuming, and I just have to assume, that this is an existing process and the process was working fine and now it stopped working. I would have to say that a couple things with that. It's probably not the wiring. It's probably not it being miswired. There may be a break in one of the wires, or maybe there was a point where the wire's frayed or it's getting motion and it just kind of wore out. The other thing is it could be a physical damage to the PLC or the HMI in its serial connection. It's possible, depending on the length of that wire going from the touch panel to the PLC, that it could have picked up some induced noise. Maybe there was a thunderstorm or something that happens, lightning strike somewhere. The induced noise was picked up, and that voltage traveled to one device or the other and possibly caused an issue. That's the only thing I can really think about in that case. If it's a new application and it never really worked, then it's most likely the wiring, I would assume. Okay, it says yes, it was working fine. Then again, I'd take a look at the actual device just to make sure the device is working. Is it possible to replace that HMI with another one to see if it is actually maybe another one will work in that place, or replace the card, or both. And this is assuming you have one available that you can put in place and try that with. But if it was working before and it's not working now, nobody got into the program and changed anything, and just one day just stopped responding, again, it's most likely some damage. The other thing that could happen, and like I said, I don't understand your situation so much, but I've seen this in doing support, that you get a guy who comes up one day and they're pushing buttons on the HMI, and they somehow or another, and I don't know how a lot of guys do this, but they do this, they find their way to the configuration menu on the HMI. And they're looking at those numbers and they're deciding, wow, there's 192, 168, 133, 64. I wonder if I change that to 65. Hit the button, close it, and then walk away. Yeah, it doesn't work anymore. And so you may want to check the IP address or the communication addresses inside the configuration settings of the HMI. When would the PLC be preferred over a remote DCS node in an environment that uses a mixture of both types? For example, we're migrating the plant from a more ACS and an Allen Bradley PLC 5 to Yokogawa on several phases. This is going to depend on who you ask. If you're going to ask your system salesman, he's certainly going to tell you you want the remote DCS node. I'm going to, and I guess I'm going to be very careful about how I answer this. It's going to be based on speed. typically your DCS remote I/O is not nearly going to be as fast as a PLC. Now, you just want to ensure that the capabilities can be done through the PLC, which in almost 99.99% of the times it can be done that way. So, and a lot of times that's what a lot of people are doing. They're putting the PLCs out there for the remote I/O, running and running the process out there. And again, if speed is not an issue, then you can use the DCS remote I/O with no problem. But the PLC gives you the capability of having a CPU out there running a program on that remote node, and while it's running, it's doing functions that maybe you don't want to tie up your DCS memory to do, whereas the DCS is just pulling data out of that PLC and making decisions based on that versus trying to run that process. But if I wouldn't put well, I'm not gonna say I wouldn't, but if you just need to read data out that is out in the field on a remote location, the remote DCS could work just fine for you with no problem, or the PLC. It just depends. But I want to just say cost can be an issue with that, and PLC is a good solution when cost is an issue. What is the typical minimum time for reading and processing an input? And again, that's going to depend on the processor, and that's going to depend on the PLC and the vendor and the quality of the processor you pick in this case. But typically, 1 millisecond is not uncommon in any type of form or fashion. If you can you're updating that input signal once every millisecond or 1,000 times per second is a very common input scan speed for a PLC. So yeah, some might be a little slower. Again, as you go into the cheaper versions, that speed is going to go down a bit. But 1 millisecond is very common and should be expected. Okay, next question. Is there any plans in the future that just deal with ladder logic programming and process control? Are there any plans in the future to just deal with ladder logic programming and process? And I think that what you're asking is there going to be any other webinars for that? Am I right in that? Hopefully that's probably, I think that's what they're asking. And I think part of that's going to be based on the request. If there's request from you guys to have more detailed type of things, and Mr. Paul's very interested in doing that, then we can certainly work something out in doing that. So that's, I guess it's kind of yes, kind of no. I don't know. It's more of a nothing planned at the moment, but could there be something planned in the future? I would say I would think so. Okay, yes, that's what I was asking. So yes, there's other things. In the terms of just Yokogawa, and I think I heard a couple things where people mentioned FAM3. Yokogawa does offer classes in-house if you have if you're using the product that you can come in and take classes. We have several engineers here in our support group that actually do programming and can actually do these type of classes. So that would, but again, just give us a call and we can see if we can work that out, I guess. Next, are there technical colleges courses or university courses that can provide training on PLC control systems from novices from the novice level, or is this on-the-job training? I learned fortan in university and can describe processes, but do not have PLC logic skills. Yeah, actually, there's probably a lot of classes, technical schools that do teach that. But I'm gonna be honest with you. You can probably go to, you can go online, and there's free stuff online. There are you can buy a course online for PLCs, ladder logic, and again, some of the vendors actually offer not so much classes, but tutorials in a book or a PDF format that you can download and read as well, and kind of work on your own with. That might be a good way of doing that. But if you're fairly technically oriented and you kind of understand relays and a little bit about PLCs, analogs, digitals, that type of thing, it's easy enough to pick up. I didn't learn ladder logic in school. I learned control theory, but ladder logic was something I didn't learn until I came to Yokogawa, and it was something that was not that difficult to pick up, and I was able to kind of run with it. Okay, so it looks like that was the last question, and we can answer any other questions that you may have via email. So it's 1 o'clock, actually a little after 1 o'clock. So again, we appreciate your time, and thanks for coming, and thanks for all the wonderful questions.
Okay, great, fantastic. Thank you very much, Clayton. We appreciate your input. Remember that you can always contact DHP for more information. Remember, we have more than 36 days of classroom training, 37 of hands-on training, 60 hours of online training. We can also provide all of that training at your facility or a facility of your choice. We also have technical services, which included the membrane element autopsies, chemical cleaning evaluations. We're doing a lot of telephone consulting, on-site consulting, and much more. So keep us in mind if you have any questions. I would like to ask you to hang around for a couple of seconds. We do appreciate you attending, but we'd like for you to answer the 3 polling questions that'll be coming up in a couple of seconds. So if you could, please won't take but 10-15 seconds to answer these questions. Thank you very much. Everybody have a good weekend. Goodbye.